Dear students, now I will explain how to perform the experiment on load flow and economic dispatch for Power System Lab 2. So the objective of this experiment is to perform load flow, optimal power flow and economic dispatch. Before you perform this experiment, you need to install either MATLAB or OCTAVE software in your system. I will explain using the OCTAVE software because it is a free software which can be downloaded. I will also show you how to use the MATPower toolbox for performing optimal power flow and load flow. The code that will be shown can also be written in Scilab, but it's with minor modifications. So to download OCTAVE, you need to open one browser. Okay, let me point you to that browser. Okay, here you will write GNU OCTAVE. It's a free software. We can download by clicking here. As you see, it is available for Linux, Mac as well as Windows. I'll show you for Windows because majority of students are using Windows OS. I had already downloaded this software, so I'll show you. So this is the installer. So after you install this, you will have two shortcuts on your desktop known as the CLI or command line interface and the graphical user interface. And I will open the graphical user interface. So before opening OCTAVE, I would suggest that you create one workspace. Okay, I have renamed that to OCTAVE WS and I have put my programs here. Okay. Now I will guide you to the OCTAVE user interface. Okay. So this is the interface for OCTAVE. I have customized it a little bit by closing many explorers. This is the file explorer where I'll go to the particular place where my workspace is there. Okay, so when I go inside this, okay, so for experiment number 4, economic dispatch load flow, we'll start with the first question. Okay, so you can see this question. I'll show you this in the manual. So if you see this manual, the theoretical background is covered in the subject power system operation and control, so we need not go through it again. So I'll show you the numerical problems that are solved using this software. The first question is the fuel cost of 2 units are given by 2 quadratic functions. We need to write a program to find the optimal schedule when the demand is 200 megawatt. So this particular question uses an iterative formula where PGI is equal to lambda minus BI by 2CI. The theory you can see in the manual as well as in your theory class. So there is a command window for this. So when I run this code, you see here the total cost in this case is 6878 and the schedule is 125 and 75 megawatt. The lambda is 45 rupees per megawatt hour or units per kilowatt hour, whatever, depending on the question. So I'll show you in OCTAVE. See this is the code that I executed by using this save file and run. Okay, once I run this code, I get this result. Okay, so now we'll see the question number 2. So there are 3 fuel cost functions. Again we have to find out the schedule. So for that I'll open the question number 2. This is question number 2. So for running this code, I'll use execute button. Now see, I have used CLC and clear at the starting, so the earlier result will be deleted, and this particular case relates to a load of 800 megawatt. Okay, but the question says to perform this for 400 as well as 450, so we'll try to do it for 450 megawatt. And if I run, so I'll get the schedule which is different, 100, 140 and 210. Okay, so next is question number 3. Okay, so this question, go to the manual to see what is the difference. Question number 3 is we have to use an iterative formula using B coefficients. So here the loss formula is given in terms of B coefficients, B11 and B22. Okay, so using this, one iterative formula must have been given to you in your theory class. So using that, we'll implement it. Okay, so we'll go to the OCTAVE console. Okay, so this is the program. So this is the iterative formula implemented in a while loop. So okay, and you can print the result. So let's run this to see. Okay, yes, you see after 5 iterations with a tolerance of around 3.6 into 10 to the minus 4, we have obtained our result of lambda 7.8, PG1 161.2 and PG2 255.6. okay, including the losses. They should include the losses also because it is an economic dispatch problem with loss. Okay, so these three programs, question number 1, 2 and 3, are related to the economic dispatch problem. Now we will go to the next questions. So the next question relates to the load flow. So as you see here, it's a very simple question. Number 4 is a simple problem with only 2 buses. Okay, this is the question with only 2 buses. Similarly, consider the system shown in figure 4.2. The data for the system is given in table 4.1 and 4.2. Again, Gauss-Seidel. So question number 4 and 5 are related to Gauss-Seidel method. Okay, whereas question number 6 is related to Newton-Raphson method. And again, question number 7 is related to fast decoupled method. The references for these problems are given at the end of the document. If you want a theoretical solution, you can find the solution from those books. So this, as you see, we need table 4. Up to table 4.3. Okay, table 4.1, 4.2 and table 4.3 as the data which is provided for this question. Also table 4.4. Okay, there might be some minor typing typos here, but you can find out the relevant data for the question. The point is that question number 4, 5, 6 and 7 implement load flow algorithm for very elemental power networks. 4 and 5 use the Gauss-Seidel method of solution, whereas question number 6 is Newton-Raphson method of solution, and question number 7 is using fast decoupled method. So now we'll go to the OCTAVE. So we'll open the question number 4, Gauss-Seidel method. We'll close the economic dispatch problems. Okay, so this is the problem which is solving the Gauss-Seidel method. Remember that we are using one program or a function for computing the Y-bus matrix. If you do not copy this file first, you will face one error. Therefore, you need to copy this file to your workspace, question number 4 Y-bus, okay, which creates the Y-bus. Then only this program will run. Okay, you need not run this program, you just need to get this function available to the earlier program. Okay, so we'll run this. Let's see. Okay, it says enter the size of the bus. It is 2 because question number 4 was a 2 bus system. So number of iterations 7. The Y bus is computed as this, and bus voltage magnitude after all the iterations came out to this in per unit, of course, and these are the bus voltage angles. So this solves the question number 4. Now I'll go to question number 5, which again was Gauss-Seidel method 1, and it's using the question number 5 Y-bus algorithm. You can have general Y-bus algorithms also, but it has been specifically done for each question so that you can understand as you are new to Y-bus formation. So we'll run question number 4, 5. So when we run question number 5, you see here the Y-bus matrix is a 4 cross 4 matrix because it's a 5 cross 5 matrix. It's because it is a 5 bus system, column 1 to 4 and 5. The after the end of the first iteration, the Gauss voltage magnitudes are given. Note that this program is only to demonstrate for a larger bus system, very first iteration of the Gauss-Seidel method. Okay. So now we will go to question number 6. Okay, and we will close this Gauss-Seidel method programs. And question number 6 in the PDF, as we have seen, it says again obtain the values at the end of first iteration, so as to demonstrate how this program works. It also uses one Y-bus function, you can see here. So you must have loaded this function with the same name. The function name must have been the same, otherwise this program will show error. Then we run this program, and as we see at the end of the first iteration, the results are given. Okay, I think here all the iterations are being calculated. Let's see inside. Yes, we are actually finding the whole solution using calculated value, scheduled value differences, and using computing the Jacobian. Okay, so you see here all these elements for Newton Raphson method see Jacob. So this Jacobian matrix is computed here, okay, with various values, okay, using the various formulas given in your textbook, and therefore it solves the Newton Raphson problem. Last question in this group is using the first decoupled method. So that is question number 7. So again for this we will, as you see, the first decoupled method is implemented here. Okay, so we'll run this. So the number of iterations, various values, voltage and magnitude are given. Next. So this is question number, as we have seen here, this is question number 7. Okay, now question number 8, 9 and 10 I'll show you. So we'll first go to the manual. So question number 8 is from the VSSUT reference book. Okay. Question number 8 from the VSSUT reference book. So this particular question is this one. Okay, this question number 8 and this question number 9, two different questions. For question number 8 we are using question number 8, it says using Gauss-Seidel method. Okay, so question number 8 is using Gauss-Seidel method, whereas question number 9 uses all the three: Gauss-Seidel, Newton Raphson, as well as fast decoupled methods. Okay, so we will solve question number 8 first. Okay, so this is the question. This belongs to the VSSUT book. So we'll run in OCTAVE. So this gives various values including power flows. Then quickly we'll go to the question number 9. Okay, question number 8 is a bigger problem. Question number 9, 10, question number 9 FD, GS, question number 9 NR, and question number 9 FD. So this implement the Gauss-Seidel method, the Newton Raphson method, as well as the first decoupled method. So we'll run one by one. Gauss-Seidel method. So this is the answer. Again Newton Raphson method will run. This is the answer. Okay, and first decoupled method, the same question will run. So this is the answer. So you see here in the first decoupled method we are showing the various values under different iterations. Okay, I'll run again. So this is question number 9, Gauss-Seidel method. Run this. This is the result including power flows. This is the Newton Raphson method, and this is the result including power various, including Jacobian. As you see, J is also calculated here, and finally using first decoupled, which shows the various iterations. Okay, various values during iterations. Okay, now coming to the last question. So the last question demonstrates use of mat power. How mat power can be downloaded, that is given here in this program itself. The instruction is given. We'll go to the manual first, go through the question. So as you see here, as it is mentioned, mat power is a free open source tool for electric power system simulation. You can download mat power from this website, matpower.org. Especially you are going to download one zip file, you need to unzip and add that to your path. Go through the mat power manual and use run pf to solve the load flow problems for 9 bus, 14 bus, 30 bus, etc. using GS and NR methods. Write here the system summary and generated data. Observe the bus data and branch flows. A code segment for your reference is given below. Basically, when you install mat power, you can simply use define constant to define various constants related to the mat power program. Then you load a particular case to the strut, case 30 or case 9 or case 14 as the required case. You give various options, the algorithm, JS, NR or FD, whatever, and depending on what results you want to print. Okay, then either you do run PF for power flow or run OPF for optimal power flow. Okay, now I'll show you how to install mat power. Okay, so we need to go to matpower.org. Okay, the latest version is matpower 8.1. You can register, get updates. Now I had already downloaded mat power, so this is a zip file that you are going to get. So what you need to do is you need to unzip it, you need to extract. So it will take a while to extract, but you will get a folder like this, mat power 8.1. But since this code was written long back when mat power 6 was available, I have added mat power 6 to my workspace. Okay, so to my OCTAVE workspace I have added mat power 6. Now I'll show you. See, when you use MATLAB, the path can be added. When you use MATLAB, the path can be added directly from the user interface. But for OCTAVE, you need to use certain commands. Okay. So I'll show you that command with which you can add this mat power to the path. Let me open that file. You need to go to the command window. Okay, let me clear this. Okay, so this is the command. This is my path where I have put the mat power folder. So here I am using add path, gen path. I'm giving that path. So everything including subfolders will be added to the MATLAB path. So unless you do this, mat power won't run. Okay, so now our mat power is added to the path. So here I am doing for a 30 bus system, running the load flow for a 30 bus system. So either you can give choice 1 for load flow or choice 2 for OPF. So let me run this. So it says enter choice. So we will first give the load flow choice. So you see various values related to the load flow are calculated, including the bus voltage magnitude, angle, etc. Now since the result is RAR, it is not shown here. You can simply write the output to a file. Okay. Next, we can do optimal power flow. Okay, so this is how the optimal power flow will run. Okay, you can explore. Now for Octave, certain things I'll say. It's like so for installing certain packages, we need to install certain packages for Octave. Okay, such as one such package is IO package. Let's see. Okay, so this loads IO package. Similarly, you need to have, you can load Optim package. Okay, now if it is available, it will be loaded, otherwise you have to install it. Now this Optim package may be necessary for this mat power. Okay, so you just check your run. If optimal power flow is not running properly, you can check for the Optim package or go through the MATLAB documentation. Okay, so this completes this question. Or the experiment. So there are 10 questions you need to run and understand the code, how economic dispatch without and incorporating losses, load flow using Gauss-Seidel, Newton-Raphson, fast decoupled is computed, and also how to use mat power for performing load flow and optimal power flow. Accordingly, you need to write the discussion and conclusion for your experiment. Thank you.